the same time. Now I give the voice to Professor Ghoniem. Yeah.
Okay, thank you very much, sir. Thank you.
Yeah.
And good afternoon, everyone. Good to see you all in the room. And let me start by thanking the seminar organizer for inviting me. I've had a great day meeting many of you and learning about the interesting work that's being done. And I told some of you that I think my last visit to Minnesota was about 15 years ago. So it's been a while, and it's been nice to come back and reconnect again. So this afternoon, I will be talking to you a bit about combustion dynamics and attempts to solve one of the outstanding problems in combustion, which is when and how do we get dynamics, how we get pressure oscillations in the system, and how we potentially could control it using some active control methodologies. I've had great, having had many great many after, and people who don't work in combustion dynamics are shown in pictures. I've also had the great fortune of being able to diversify my research several areas during my career. So I still do combustion, both simulation and experimental work, but I've also worked extensively, especially in the early part of my career, on computational fluid dynamics. I was one of the first to introduce Lagrangian methods, particle-based methods in CFD. More lately, I would say over the past 15 years or so, I became interested in diversifying my research into the energy area. I worked a lot on carbon capture technologies or carbon capture processes, where we used oxy-combustion, which is a kind of a natural extension to my research in combustion, but I also worked on areas of oxygen production, air separation, which is an important area in oxy-combustion in general. We worked for a while on coal, actually using oxy-combustion, and we developed new methods for efficiently burning coal and oxygen. Fortunately, coal has not been very popular, so we gave that up. We also worked on newer technologies for oxy-combustion, like what's known as chemical looping technologies, where you use metal oxides to separate oxygen and burn fuels. Great, fantastic technology. We've done a lot of progress in it. Still considered a bit more expensive. It hasn't been applied commercially at scale, but I'm sure it will get there somewhere. More recently, I would say over the past 10 years, I also started looking at fuel production, both biofuels as well as hydrogen. And the combustion work continues, and the reason it continues is because I don't believe, and many thought leaders don't believe, that everything in our life will be electrified. So we still will need to burn fuels, whether we want to do long distance transportation, whether we want to do industry that needs high temperature like cement and steel, or we need to store energy. A great deal of storing electricity is in the form of fuels. So combustion technology is going to be around for many years to come. Maybe we will not burn the same fuels we burn today. Maybe we'll burn other fuels, hydrogen, ammonia, maybe other fuels will be invented, will be sensitized, but they will be very much part of our energy systems. And combustion technology has benefited greatly from combustion science. So those of you who are currently studying combustion can review combustion theory. It's very highly developed and well synthesized and systematized body of knowledge that was developed over the year, largely by taking advantage of three different approaches that we work with. One is theory, obviously developing theory for combustion science. analytical methods, asymptotic expansions, and so on. The other two that have revolutionized the field are diagnostics and computation. Being able to measure at the particle level very fast anything you want to measure, and being able to compute at many scales and with significant complexity in the physics you're computing, has made it possible to really dig deep and learn more about what's going in combustion. So this day and age, when you study a technology, you do what I call throw the kitchen sink at it, right? Do analysis, do computation, do experiment, try to apply as many tools as you can to figure out complex puzzles, how things burn, how they convert chemical energy to thermal energy, what comes out of it at the tail end, has become the trend. And what I'd like to do today is take you through a journey in which we did that. And we did that in this particular problem of combustion dynamics that I will define in a second. But by halfway through the talk, you will realize that it wasn't possible to do everything we wanted to do without having very good experiments, without having theory, and without applying very powerful numerical methods. Towards the end of the talk, hopefully you will hear how we're trying to use that understanding to control the problem that we have, which is a combustion dynamics. So hopefully you will go through sort of a full cycle of defining a problem, trying to solve it, getting insight, and moving towards application. So combustion dynamics is encountered constantly in continuous combustion systems. When you have a system burning, like a gas turbine system or like a continuous burner, you have the chance of the flames or the heat release zones activating an acoustic field. It's like you're blowing in an organ pipe, but instead of blowing, you're burning. So you're increasing the volume flow rate in the system. Once you excite that acoustic field, the acoustic field itself is going to send both pressure and velocity waves through the combustion zone. So the combustion zone is going to be affected by the acoustic wave. If the acoustic waves and the combustion field synchronize or resonate, you get a resonance by which each one feeds on the other one, and you get oscillations to grow to very dangerous levels. That's what's known as thermoacoustic instability. And as I said, it's encountered in many applications, all the way from rockets to gas turbines to industrial burners. And it's been one of those outstanding problems that we always talk about when we talk about outstanding problems in combustion. So here is a typical swirl stabilized combustor. What we see is pre-mixed gases coming from here, from a swirler. Combustion is stabilized in this zone, but hopefully you saw that it's not really stabilized. The flames are puffing. And on the other side, you see some of our attempt to compute that problem, where again, the flames are exhibiting, that's sort of a demarcation of a flame line, exhibiting these oscillations. And the oscillation is coming from that coupling that I identified or talked about before. Believe it or not, the problem was defined in the 1800s by Lord Rayleigh, one of the grandfathers of acoustics, where he understood that if you have heat release zones embedded in acoustic fields, you can get resonance. And if you get resonance, the pressure oscillations will grow. And when he came up with a mathematical representation of this problem, that if the integral of the heat release perturbation multiplied by the pressure oscillations, maybe I can use my thing here, okay. Pressure oscillations multiplied by the heat release oscillations. If the integral of that over space and time is positive, instability will grow. Until today, this is known as the Rayleigh criterion, and it's always used as a diagnostics for whether combustion instability is present or not. Another way of posing the same thing is if the phase angle between heat release oscillation and pressure oscillation is less than 90 degrees, you get positive interactions. So either the phase angle or the integral can be used. What that says is that's a diagnostics for the phenomenon, but it doesn't tell us whether the phenomenon will happen or not, because the phenomenon will happen only if the acoustic waves are indeed able to impact the combustion process. And that has been one of the outstanding issues, is when and how would the acoustic field impact the combustion process. When we started tackling this problem, and again, we've been working on it for a while, these experiments were done in early 2010 or so. We started using PIV techniques to get the velocity field under unsteady condition and an average. A swirling flow will always produce a recirculation zone that actually stabilizes the flame. We used cliff techniques to look at the flame front. These fire-looking things are actually the flame front under unsteadiness that's encountered. Obviously, we use the experiment to define what visually what the flame looked like, but we also used computations. And what we gathered in the beginning, that none of these tools by itself will be good enough, because the experiment is great, that's the reality, and that's what nature shows us, but we cannot get all the data and all information we need from the experiment. So we needed to go to computing. Computing has idealization, so it cannot be relied on by itself, but it gives us incredible insight mechanistically into what's going on, because we can compute everything. So the experimental setup is a very straightforward combustion tunnel. We have pre-mixed gases, think methane air, for instance, going through a swirl zone here. Here is an enlargement of the same thing. The swirling flow goes through a sudden expansion. It encounters what's known as vortex breakdown. It forms a very strong, large recirculation zone here that circulate the products to hold the flame, and the flame here is shown from the experimental PIV, PLIF, in place as long as conditions are compatible with stable flame. So that is the experimental setup we had. And when we ran this experiment, we changed the equivalence ratio, the fuel concentration in the premixed gases. So our control parameter here was how much fuel we put into the system. So as you know from your combustion basics, you can start with lean condition, low equivalence ratio, and you can go all the way up to stoichiometric condition. And when we ran the experiment, like many others work in this field, it's not only my group, at different equivalence ratio, and measured the pressure oscillation. So this is RMS value of the pressure oscillation. At different equivalence ratio, we encounter in the beginning at the relatively lean condition, relatively quiet kind of background noise type situation, but at some equivalence ratio, the pressure oscillation jumped extensively. It became very large. You can look at it here. This is a sound pressure level as a function of the equivalence ratio. At some point, it starts to grow significantly and kind of goes steady at some point at these very high pressure oscillation. That's what we call unstable burning. That's when you start the flame puffing, going back and forth like you saw, and you hear very loud noise coming out of the combustor. So this combustor is unstable, as we wanted it to be, and we wanted to know why it's unstable and what makes it go unstable at these conditions. So first thing that you do when you encounter a problem like this is to start with what I call the base case. What is the base case? So the base case can happen if you decouple the acoustics from the combustion field. So remember, where the flame is sitting here, and when it starts to oscillate, it resonates with the acoustics, so the acoustics help it resonate more. How about removing the acoustic field? How do you remove the acoustic field? We chop the combustor down to a much smaller length. So we don't allow resonance at the favorite acoustic frequency of the system. So we stop resonance from happening, and we look at the flame. And we started looking at these flames as we go from lean conditions up here to richer condition. At lean condition, the flame is very long, this very long V flames, because at lean condition, the flame speed is very low. As we increase it, the flame starts to grow wider, more intense, wider, further. Here's the widest it can get, and then it switches from what we call a V flame, a flame opening like this, into a flame that's also stabilized near the wall. Different people call these flames differently. We call them flame 4 for historical reason. In France, they call them the M flame. They call these the V flame, and they call these the M flame, because they look like an M shape. So this is sort of the base case without any coupling, without any oscillation. When we coupled the system, we put in the acoustic pipe that's part of the original combustor again, and we ran the system. We saw very similar average flames coming up. So these are the coupled flames, and you can judge for yourself how much these look like these. But with acoustic coupling, the sound pressure level is very low. Here is the pressure oscillation. Then once all of a sudden the pressure oscillations start to jump, and we get this first instability. You get another quiet zone, then you get a second instability that's even worse. On the other hand, oops, I don't know why I lost the slide. On the other hand, this is a noisy combustor that's about to self-destruct. This is quiet one, but this also allows acoustic coupling. The other one does not. What we concluded is that the base flow does not change when you couple it with the acoustic field. That the underlying flow, the underlying combustion process did not change with the presence of acoustics. Something else happened, and the question became, what else happened? Just to add a bit more fuel to the fire, no pun intended, we tried the setup with different fuels. For instance, we use hydrogen instead of methane. We use hydrogen and oxygen instead of, and methane instead of pure methane. We tried syngas with different composition. We tried oxygen as an oxidizer instead of air. And we would get the same transition, the same flame shapes. Here are the flame shapes going from this long V lazy type to a much more active type. We get very similar PIVs, similar flow field on average, and similar instantaneous flame structures from the experiment. So these changes will always be there. Of course, they may be different. They may occur under different conditions when you change the fuel or the oxidizer. You would expect that if you change the fuel or oxidizer, condition at which you get into unstable regime change. But you get into unstable regime, and you get into unstable regime once the flame looks a certain way. Once it goes from that flame 3 to flame 4, you get unstable. So we started thinking, what is going on here that would make the flame, when it couples, go unstable? And we started digging into the theory a bit. One major model for turbulence interactions with flames is known as the strained flame configuration. So flames normally propagate on their own. If you add turbulence to them, turbulence will start to tear them up and stretch them and curve them and do all kinds of things to them. Fundamentally, the most important interaction is embedded in what's called strained flame. And what a strained flame is a flame subjected to a positive velocity gradient along its own structure. So you take a flame and the flow starts to pull it in its own direction. Once it starts to do this, it's impacting the balance between transport and chemistry. Because once you pull on it, the transport fluxes change. And then transport fluxes change, the transport rate change, and you may get into a situation where the transport gain flux is, or transport time scale is no longer accepted by chemistry, because chemistry has its own time scale. If you stretch a flame too much, you extinguish it, you kill it. Okay, and that has been very well known, a very, very, very well developed theory to show that, and very well developed computational methods that will show that as you change the stretch rate on a flame, its temperature starts to drop, and at a certain point it dies. Below that point, it can never survive. Physically, at that point, you're pushing too much reactants into the flame. The chemistry cannot keep up with it, so the chemistry stops, and if the chemistry stops, you no longer have combustion. That's what's known as the extinction limit, and the extinction limit plays that role as one way to define interaction between the combustion process and the turbulent process. And again, all of this has been studied in detail in the turbulent flame theory to establish conditions under which these flames extinguish. And the reason why we thought that theory should play a role here is because what we find is at some point this change in the flame configuration or flame structure is associated with burning being possible in areas where it wasn't possible before. So you push the flame in areas, makes it much more compact, much stronger where it shouldn't have been. The only way that can happen is if the flame gets too strong, it's no longer being extinguished in these areas. That was kind of like the inspiration for thinking about the theory. And we wanted to set out to see whether this theory makes sense or not. That the extinction of flames in certain areas of the flow is the reason why under some condition you get instability or coupling, and under other conditions you don't. We did it in two different setups. I'm not going to talk about this setup for too long, but that was the first setup we did it on because it's a planar, what's known as step-stabilized combustor. It's a bit easier to measure in it. It's a bit easier to get the velocity field from which you can get the strain rate, which is defined here in terms of velocity gradient. And indeed, it did show that it's possible to use the strain rate to identify the point where that sort of transition from stable to unstable conditions occur. So the strain rate is a property of the mixture, only a property of the mixture, as well as the operating condition, of course, the temperature and pressure. So if we can use that property across all the fuels we used and across all the oxidizer stream we used, to actually scale the data from different fuels and from different oxidizers, such that all the characteristic curves that we used to get individually can almost collapse on the same line as a function of a strain parameter. This is shown much better. Here are different characteristic transition curves for the pressure as a function of the equivalence ratio. We calculate the extinction strain under different equivalence ratio and scale all of this data with respect to that extinction strain. And we see all the data collapse on each other. There is one value for the extinction strain rate, irrespective of the fuel, that the system goes unstable on. And that was a very interesting revelation. It's kind of a scaling argument. If you look at the history of physics, history of science, scaling has been one of the most important tools people use to develop physics. And when you can bring it into a problem as complex as this, is very gratifying. It's almost like a breakthrough. How can you take very complex data like this and be able to present them on one curve? Potentially, this one curve not only will apply for these fuels, but will apply for other fuels, because the extension strain rate doesn't really care about the fuel. It's a function of the fuel, but once you get that function right, the rest of it doesn't matter. So that was our sort of our first kind of, if you like, breakthrough in this thing. The second one was exactly the question that I was trying to answer before. Why does the strain rate play a role? Well, here is the flame being visualized by two cameras. This is an isometric flow, so we have two cameras looking from top and the side and showing what I would first call as flame 3, the V flame, very intense. Then after a while, you see the outside catching fire. So here's V flame. After a while, you see, boom, the outside catches a fire. When the outside catches a fire, the instability kicks in. So this has very much to do with enabling this flame to propagate into this area, which initially could not support this combustion. These are the same thing, but still and under unsteady condition. So this is our V flame, and this is our basic W flame, when we're not only burning inside in the inside shear layer, but we're also burning on the outside shear layer, providing that intensity of burning and providing the support for the instability. So we immediately decided that the real question now to answer is, why does the flame jump from the inside shear layer to the outside shear layer? What is in the combustion process that makes that happen? That's when we switched to computing. So we took one of our favorite codes for turbulent combustion with some reasonable chemistry for methane, but reduced so that we can do LES type calculation. So that is our swirling vein. This is the inlet pipe, this is the exit pipe, and that's the sudden expansion. And we started running this code. And we started running a code like this. The first thing you want to see is, you get the overall features and you get this transition. And the answer was not yes, that we're able to see what under some similar condition, what the experiment shows and what the simulation show. Also, that as we started increasing the equivalence ratio of fuel, the flame switched from that V shape into that M shape, or from the flame 3 to the flame 4. So that gave us confidence that the simulation, all simulations have simplification in them, so you need to check before you're comfortable with the interpretation of the data, that you're at least getting the basic features right. This showed us that indeed we can get the basic feature right, that with increasing the equivalence ratio, we can get the switch from one flame to another. So I said, all right, well, let's look further. Let's look whether we can learn a bit more from the dynamics of that flow. Why would the flame want to jump from one location to another? So this kind of the underlying major vortical structure. It's a corkscrew vortex that starts at the swirling zone and forms almost like what looks like a corkscrew. And this is the vortex that takes that flame and spins it around. When you see these holes in the experiment, there's the impact of the penetration of that vortex. So here, for the fun of it, there's a whole bunch of movies. If I do it correctly, you'll be able to see them. If not, yes, here we go. So this is the flame front visualized by a particular temperature. And these are the swirl vein. The flame is actually stabilized on the aerodynamic body here. And here we're just showing sections to capture the vorticity field. Look at this corkscrew vortical spins. And here the same thing showing the cross-section of that vortex and how it's interacting with the flame. So, okay, so there's a very important strong vorticity field with associated strains and so on that's governing the stabilization of the flame. Now, here is another representation of the same movie. This takes a bit of careful watching, so please pay attention. Whereas the calculation will show you the transition of the flame from 3 to 4. So I'm going to advance so that we can watch it. And the first one shows one representation, which is a maximum heat release, kind of representation of flame. The second one shows the temperature contours. So the temperature contours here, the flame was hot, that is the deep flame, and the outside zone was cold. And now we're increasing the equivalence ratio gradually. And as you hit a certain point, outside area got inflamed. And now we're burning inside and outside. And the maximum heat release zone folded. This is, believe it or not, this is the fold that stabilizes inside, goes out, and stabilizes outside. So it literally is two flames folded on each other. So what this is showing is, again, how the simulation are capturing this idea of the flame propagating from the inside out, and how again, just for the heck of it, I'm going to show you this one more time to show that folding process happening. So that is the flame 3, the V stabilized on the inner shear layer of the inner recirculation zone. And at some point, you will start to see the flame folding backward, propagating almost along the wall, forming that end flame. So now the flame is stabilized not only outside, but inside. And that fold, the formation of that fold and the stabilization of that burning zone outside is what we assigned, or what we hypothesized is the demarcation of stable versus unstable flame. Going from one type of flame to another, from quiet operation into dangerous operation. So it's very, very important to see exactly what's happening here. So we started looking at the numerical data. And again, this starts as a movie, but it will hopefully. Okay, so that is a flame surface. That's just one line, maximum heat release line. That's advancing. Now, from all what we've seen so far, is all that happening here, that the flame will fold around here to come back and stabilize itself on this point, so we get two flames. So we started taking measurements of the dominant strain rate at that point. Remember, we defined the strain rate as what's determining the interaction between the flow and the flame. And we wanted to know whether the dominant strain divided by the extinction strain rate in this zone changes its character or not as we advance the flow. So the answer is here. You will see all of them coming down. So the dominant strain divided by the extinction strain rate is coming down, which means that the extinction rate is going up. Makes sense, because we're adding more fuel, but the flame is stronger. So as the flame gets stronger, it's able to overcome the strain rates here that will now extinguish it. But as the flame gets stronger, it will move into that zone. So I will run the movie just to show. Okay, so at that zone where we're calculating within that box, there's the fold forming, heating into the, so now all the gases that are coming out of here are burning through these two flames, much more intense than it used to be. And at that point, we find that the extinction strain rate is becoming high. It's overcoming the fluid strain. So the flame is surviving conditions under which it couldn't survive before. So that was very nice. That was very satisfying, that what we sort of hypothesized from looking at the experiment and reviewing some of the theory was proven right. what do you do with all of this? If I go to United Technology or General Electric that builds these combustors, what do I tell them? I tell them that I discovered that the operation of this combustor can be determined by two characteristic time scales. One of them is the flame time scale. The strain rate is 1 over T, so 1 out of the strain rate is a time scale for combustion. And the other one is the flow time scale, because the flow is the one that is generating the strain. Okay, remember the flow is inducing the strain, the flame is responding to it. And I can take all the data I can get on this combustor for different fuels and different oxidizers and define a plane that separates plane 3 from plane 4, the V flame from the N flame. If I operate here, stable. If I operate here, unstable. So we think that's a very valuable result for an industrialist designing a combustor, wanting to know under what condition his or her combustor will go unstable. If you change the equivalence ratio, you will change the flow characteristic time. If you change the flow conditions, you will change the characteristic flow time. If you land here, forget it. It will self-destruct. If you land here, you will be all right. So I'm showing a summary of how the data is synthesized, but with the objective of showing that our effort here was not just to get sort of comfortable with understanding the physics from both the experiments and the theory and the numerics, as well as trying to solve an academic puzzle, but also to present some results that could hopefully be useful for people who design these combustors and operate them, figure out how to operate them safely. The theoretical analysis went on. I'm probably going to skip this one, looking into what's known as scatter plots for turbulent flames. That also goes into turbulent flame theory in trying to bound a turbulent flame by some bunch of laminar flames that we know how to study better and draw the similarity between them and the laminar flames to learn a bit more about them. The scatter plot analysis proved the same thing. We also extended the same concept in trying to scale things. Again, remember, my key point here is scaling. You're a good engineer and scale things well, you make a lot of money because your result can be used by many, many, many more than the experiment or the theory you developed. So when we showed that scaling can work for dividing the operational domain between stable and unstable, said, well, how about applying it to other things? For instance, always talk about the size of recirculation zones forming downstream of swirl system. And the size of the recirculation zone is important because that's what holds the combustion stable. We showed that, again, within a reasonably wide range of condition, we can scale the size of the recirculation zone to the extension strain rate of these flows, also on a straight line like this. I spent about 10 more minutes maximum in showing our next venture. So the venture so far has been understand combustion dynamics, understand the source of combustion dynamics, define the mechanism responsible for it, define conditions under which it works or not, try to come up with some scaling argument for how you can use data from one experiment to help the other. I should stop and say that the scaling is not only useful for operating within the range of conditions that we use. Of course, you have to always validate the statement, but I would argue that if you change the fuel into radically different fuel, for instance, switching from hydrocarbon to hydrogen or hydrocarbon to ammonia, hopefully the scaling will persist. We haven't done this experiment yet. That's still under consideration. But that's one of the things that we're hoping to do, be able to carry over all the knowledge that we developed for hydrocarbon flames into other types of flames without having to redo everything. So that's obviously a pain. What we're trying to do here and now, and in this next few slides, is figure out whether we can control the instability. We know that the combustor will go unstable, right? Unfortunately, because it self-destructs if you go unstable, or you have to stop the operation. Active combustion control has been around for many years, even in my own group since late 90s. In fact, Professor Strakowski, the project that we were in ONR, was the same set of issues. How can we understand combustion dynamics to a point where we apply active control to it? And we have been successful doing this using fuel modulation, using a concept that was popularized by a well-known acoustician in the UK, unfortunately passed away, known as anti-sound. Anti-sound is the same idea you use when you use headphones in planes. Any of you have the Bose headphone? Bose headphone does anti-sound. It measures the sound in environmental sound, produces sound waves with the opposite phase, so that when the two waves meet, they destruct each other. And that's what's known as anti-sound. Since acoustic instability is based on sound waves interacting with flame, potentially if you produce sound waves that counter the effect of the natural sound waves, you can suppress the instability. And indeed, it turns out to be true. Question is, how do you produce sound waves? You cannot use loudspeakers because you need massive, humongous loudspeakers for these kinds of pressures. We use fuel modulation. We use fuel injectors that modulate the fuel into the combustor so that we make the combustion process itself unsteady. So the combustion process itself produces its own anti-sound wave that suppresses the existing waves. That works very well, except it works only if the instability frequency is relatively low. Because mechanical modulation has inertia. You cannot go to very high frequency. Very difficult to go to 1,000 hertz, for instance, with a mechanical actuator. You lose authority very quickly. Recent trend has been try to use plasma, in particular, nano-pulsed plasma that can NPR and nano-pulsed repetitive plasma that can fire electric fields at very high frequency. We're talking about frequencies and kilohertz. So if you have an electric field that you can fire, electric field is very strong, 20 kilovolts. 10 kilovolt works also sometimes. It depends on the condition. But if you're firing an electric field with this volt, but at these frequencies, then you have very high frequency in the field. You have very high authority on the field, temporal. What we don't know is whether the electric field can affect the flame. Well, we know the electric field can affect flames because they ionize the gas and change the chemistry. So we knew that well, we still know, this is work in progress. It's not finished. I just wanted to give you up-to-date information. We knew it can, but can it affect it in this environment where we have these dynamics and instabilities and complex interaction? So the work has been starting first in the lab, as always, on the same combustor, apply plasma, NPR, that this non-thermal plasma or non-equilibrium plasma or nanosecond repetitive discharge plasma to the field by mounting an electrode on the center body and another one on the body of the outer edge of the combustor, and operate with no plasma and with plasma. Now I'm showing the movie here for both of them, the same thing. The top one, again, the flame is bouncing back and forth like mad, but you also see the pressure, about 4,000 Pascal pressure oscillation. With the plasma fired, at least without too much interference, we get a factor of about 2 drop in the pressure oscillation. So the plasma is able to impact the flow, not 100%, that's not ideal, that's just a 50% reduction in amplitude. But we don't know why it's suppressing the instability, and we don't know how it's interacting with that flow. So as just a recap, you can indeed reduce the sound pressure level, sometimes by a factor of 2, sometimes by a factor of 4. If you're lucky and with very strong electric field, you can almost suppress the instability. What we don't know yet is why it suppresses the instability. Why do we see that reduction? So the first thing we started looking at is, does the plasma produce anti-sound? Does it produce this interference that kills existing oscillation? So on the top part of the slide is still the same movie, showing both the pressure wave and the flame oscillation. And this dot is just showing the time synchronization between the two. What you see is when the dot is at maximum pressure, the flame is most luminous. So you have in-phase operation between combustion and the pressure. Really, criterion love this. He said this is the most unstable case. The bottom one is when we fire the plasma on this system. What you immediately see is when the pressure is maximum, flame almost does not appear. Don't worry about it. This is the plasma fire. This is the flame. Okay, it's a bit confusing. That's one of the problems working in this angle. It takes a while to get used to the markation. So when the pressure is maximum, no flame. The pressure is minimum, you see the flame. So it almost goes to the opposite of the Rayleigh criterion. So it's interfering. It's doing something. It is changing the dynamics. How and why is yet to be determined. But it's changing the dynamics, and it's showing hope that indeed, as you go from the without plasma to the with plasma, you change the phase angle between P prime and U prime so much so that you can get to a domain where you can suppress the instability. So the first thing we had to study when we got there, how does the plasma impact the combustion process? The plasma is nothing but subjecting the gas to a voltage. That's all what there is there. Whether the voltage will be able to discharge energy into the flow or not, we don't know. It depends on whether we break down the gas or not, ionize the gas or not. And indeed, when we started looking at the interaction between the plasma we're firing and the flow, we found that at least there are 2 modes the plasma can discharge. It can discharge as what's known as a spark, and you get this very, very bright area within the red box, or what's known as a streamer. It's a very weak breakdown where you hardly see the light. But that happens, the spark happens when the flame is very strong, and the streamer happens when the flame is weak. And that was why we don't know. The plasma discharges best when you have this E over N, the voltage divided by the number density in the field high. Maybe when the flame is out, the gas is hot and the density is low, so N is high, so the energy is high. That's what we think is happening, but that's yet to be determined. Again, when you look at the plasma energy deposited in the field as a function of the pressure, find that the plasma energy is somewhat consistent with the pressure oscillation. So the plasma is definitely impacted by the state of the gas. We ran different plasma conditions. different volt and different frequency. Remember, these are the two parameters we can control. How much volt you put in and the frequency, the repetitive frequency. Found that as you increase the volt, the energy associated with the plasma, which is this red, the red is the spark mode, the energetic mode, increases. And with the frequency, the duration of it in the cycle, this is a 360-degree cycle, and the duration increases. So with stronger plasma, with higher voltage, and with higher repetitive frequency, you get more interaction because you get more energy deposited in the field. The discharge depends on the field. It's unfortunate, actually, because it kind of limits our authority a bit until we understand exactly how that interaction happens, but it is part of the nature of it. Also, as you change condition, remember we're discharging, boom, 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 but the fluid is responding, and sometimes the fluid responds when the pressure is rising, sometimes it responds when the pressure is dropping. Sometimes it's only consistent, like in this case, only when rising, and here it's when rising and dropping. That also depends on the field. Ultimately, what we found is that we need to have a strong enough field that you get large discharge deposition in most of the 360 degrees of the instability cycle, and you need to have it such that the discharge is strongest anti-phase with the pressure. These are the conditions that will lead to filling the instability. Exactly why it's under investigation. Here is the change in the instability reduction with the fraction of the discharge in the spark mode, not in stream mode, means in spark mode. So the more sparking you get in your flow, the higher the instability suppression will get. So we're accumulating these sort of bits and pieces of mechanistic information about what was going on in order to see how we can hopefully optimize the discharge to get the maximum authority of control. So let me wrap up and leave some time for questions. Trying to give you the student body few messages. One is, if you're trying to solve a complex problem, do not rely on one tool only. Better to have multiple tools at your disposal to see whether you can actually look at the problem from different angles. That's what we did when we did experimental work and numerical work and pulled in some theory to help tie the two together in a meaningful way. Theory is very, very important to get you that mechanistic feeling. Of course, theory is always done with extreme simplification, so you cannot use it by itself. In the combustion and instability domain for these well-stabilized flows that are widely used, we found that there are specific equivalence ratio at which we get the transition, that this equivalence ratio, the flame switches its shape from this V flame to this N flame or 3 to 4 flame, always associated with this point. And we found that the reason why it does that is because the flame now starts to be able to overcome the impact of strain field and extinction and burn more intensely closer to the stabilization point. And out of that, we were able to scale data for different fuels, different oxidizer over a wide range of conditions using the extinction strain rate as a scaling parameter. So the canonical, the eigenvalue of the problem here is the strain rate that allows you to do the scaling. Hopefully, the practical implication is that we can create one performance map for the combustor that divides its domain of operation into two, stable and unstable, as function of the extinction restraint rate and or time scale, extinction time scale, and the flow time scale. Finally, coverage of plasma. This is still work in progress, so it's not final. We think plasma does have the chance of acting as an actuator to suppress the instability. It does, with the right authority, suppress the pressure oscillation, but we still need much more study to understand mechanistically what's going on in order to do the actuation more smartly, so to speak, to both minimize the energy for actuation and maximize the gain. With that, I'd like to stop. Again, thanking my students. If you want to do so much work, you better have good students like you. I've been fortunate that I have had good students, and that's how we were able to do so much work. Some of the sponsors, and I'm done, but I'll be happy to entertain questions.
So thanks, Professor Ghoniem, for the very nice talk. You should trigger a lot of questions to me already, and let the audience ask questions first. Any questions?
I guess I'll get started on the questions. Do some time for students too, but would you mind going back to the beautiful linear correlation that you had with the time scales? I had just a couple of questions about that. So, if we can talk about the diameter of the most significant result here, this one. Yeah. So the question is, you have on the denominator or on the x-axis, you have is that the diameter of the outer diameter of the
That's the diameter of the sudden expansion cross section.
Of the sudden expansion.
Yeah, the diameter coming in. Yeah.
So does it matter the relative diameter between where the swirl comes out and the big diameter? Is there a ratio that's important there?
It does matter. Just not to be used car salesman, this has to be produced for every combustor configuration. So this depends on the combustor configuration. If I make it wider, what will happen is that the heat loss at the wall will change. So the heat loss at the wall, where the flames start to kind of lick that wall, affects the extinction strain rate at that point. That affects the local temperature at that point. Okay. So my selling point in this is this applies to a single configuration across fuels and across operating conditions.
With a single swirl ratio as well.
No, actually, the swirl ratio is embedded in the
Oh, there it is. Sorry,
yeah,
it's right there.
Yeah, it's embedded here. So
all right, and then one more question about this is that when does transition from flame 3 to 4 lead to extinction as opposed to instability?
Oh no! In this domain, it never leads to extinction.
Never.
So the extinction here is the difference between flames burning out here and not burning out here.
Right.
So the extinction happens as I move this way. I no longer can see flames burning in the recirculation zone.
You don't see them anymore.
In the outside zone. So the flame spreads out more. Okay, it gets longer.
But does it ever reach to a point where it burns back and then doesn't establish and doesn't go back and forth?
No, because to get it there, we increase the equivalence ratio.
Yeah.
So this is a stronger flame. Yeah.
Okay.
So as you can see the brightness, right? This is definitely higher equivalence ratio. The further I go out here, the more the thing will shake because the pressure amplitude will increase.
So a higher equivalence ratio will lead to greater instability.
Yes. Yes, absolutely.
Yep.
Yes, absolutely. So only way to get that flame to be the combustion to be stable is to scale back in the equivalence ratio before you get to flammability, lean flammability. Yeah.
Okay.
But then when you scale back, you get into this very long blaze of flame, which means that the combustor will be very, very long. So that's not practical.
Right.
And that, I mean, the significance of this is trying to see under practical condition, how can we suppress the instability? Practical flames, you know, the more compact the better.
Right. Thank you.
Any other questions, especially from students? We hurry the students. Okay,
Yeah.
please go ahead.
What is the thermal boundary condition used for the wall?
What's that?
The thermal boundary condition.
Or the thermal boundary condition.
A thermal bound.
A thermal boundary condition. Yeah. 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 It is a heat loss.
Heat loss.
Convective heat loss.
Was
That's
that-
a very good question. Yeah. That's a very good question because unless you do this, this becomes adiabatic
Exactly,
and it will burn anytime.
exactly.
That's exactly very good question. Actually, there's a little story about that. They were applying a diabetic condition, not getting the transition. Then we said, let's go back to the experiment and measure the temperature
The
in
wall-
that zone, not to the wall, the gas
Gas.
in the recirculation zone.
Yeah.
And it turned out to be like 400 degrees, 400 Kelvin. It wasn't that high, yeah. It was pretty cool. You don't expect when you have such intense burning downstream that the gas there will be that cold. But because of the, you know, it's a metal combustor, right? It's using heat like mad. And that was immediately pointed to the need to apply heat loss boundary condition to get the transition.
So you usually consider conjugate heat loss.
Yes, absolutely. Yeah.
Great.
Yeah, I'd be happy to send you a couple of papers on that because that also generated, we're branching off, but these are the questions. It generated the whole, another set of studies about the impact quantity transfer on flame stabilization, laminar and turbulent. So we have these couple of those.
We recently did a bunch of studies, same propagating through narrow tubes.
Yeah.
Found out the behavior is pretty different when you employ isothermal
Absolutely.
adiabatic walls.
But-
Completely.
And it's interesting because people knew that narrow tube, of course, you know, you kill the flames when you put them in a narrow tube. But that conventional wisdom was a big tube, it doesn't matter that much. I mean, this is that big,
That big, we're in that.
but it's still, his losses were very important.
Practically in the experiment, would it still be, you cannot treat it as an adiabatic or an isothermal practically in the experiment, but it's still.
Oh, I guess you can put insulation outside if you,
Oh.
yeah, if you wanted to study the diabetic case, yeah, you can definitely put insulation. But we didn't. My fear is that the metal may melt. Because when you run experiment like this, you have ratio, metal glue. And so after a while, you have to turn it off. So definitely a diabetic condition would be.
Thank you, that answers.
Yeah, sure.
Any other questions?
Yeah.
Yes. On the plasma part, maybe this is more a suggestion than a question, but
Yeah.
it could be very interesting to forward the electrodes with AC waveforms instead of nanosecond pulse.
Uh-huh.
And the way I bring this up is because nanosecond historically is for chemistry, nanosecond timescales.
Yeah.
But since you are looking at short waves, like AC, an AC power supply that you have defined, and you can change the frequency, could be interesting to look at that frequency of the AC waveform with respect to the AC frequency of your pressure waves. And your plasma there, I expect it to be mostly streamer, no spark at all.
Yeah, I mean, it's definitely worth trying. My initial, but that's kind of intuitive response is what we're trying to do with the plasma is have the plasma activate combustion process to produce the pressure. That because this has always been the struggle with these. These pressure waves are okay. So we're talking about 4,000 Pascal. So 3 to 4% of the amplitude. It's pretty strong. way stronger than you used to maybe sound wavelength. If we're trying to counter them, unless we have the flow itself reduce pressure waves that can counter that, we will need a huge amount of energy. That would be my theory. And it's definitely worth trying, and we can learn something from it. But our sort of strategy has always, can we activate the flow so that the response of the flow will be to generate pressure waves of the same order of magnitude of the instability. So nanopulse is hopefully, given the chemistry, given the who knows, I think it's just doing the ionization to the chemistry. And hopefully that initiating the combustion of the certain phase to counter the different.
Thanks. Other questions?
Yes, sir.
I'm looking at your picture of plane 4.
Yeah.
And it looks to me like there's a circulation zone in the middle, right? But what I'm wondering is what's preventing the plane from back propagating further into the corner of circulation zone of the guys?
It actually does. You mean here? Yeah, it does. It just faint. It's just very faint. I mean, okay. So the outer recirculation zone is a whole bunch of products, right, trapped by that recirculation zone with reactants penetrating into the membrane. And the reactants do penetrate all the way to the former, but less and less and less of them. And the light just faints so that you cannot see it. But I can show you a picture that will show that you're right with the pliff, because with the pliff we can why it doesn't respond. Oh, maybe I do this. Okay. Aha, here it is. Yeah. So you see, if you focus on it, see the fire?
Yeah, but periodically like that.
Yeah, because it's periodic because it's spinning, right? So it spins in and out, that helical corkscrew vortex.
It must have to rain and then fill. And
Exactly. That's another way of thinking about it. It fills with reactants, burns, and ejects. Reactant, burns, and ejects. That's why on average, you see a bit of a faint color here, but instantaneously it does that.
And then the hot gas.
And here too, this is an instantaneous picture. Here is the boundary of the flame, and it extends all the way.
And the hot gases are then able to escape without putting the flame out.
Right, exactly. That's okay. Remember the corkscrew? The corkscrew is literally taking things in and moving forward. So it's like he's sweeping and moving forward. That's the nature of that corkscrew. So instantaneously, you will see the outer zone filled, but then the flow is pushing forward. So it takes that gas out, and the fresh mixture behind it refills it.
Thank you.
Okay, I guess we run out of time, but yeah, you could ask, unless that's a very short question, maybe. Okay, go ahead.
Yeah, maybe just, I don't know if I understood this correctly, in the other part, we were talking about the plasma triggering, well, generating anti-sound. Is this a closed loop way of doing this, or are you just picking pulse frequency?
It's not a closed loop yet. No, it's all people. Yeah. But hopefully our next step, as we understand what the people are impacted. So everything we should here is said or just apply certain voltage and pulse it at this frequency and so it happens. And then we change the voltage and there is no loop. The closed loop work was done with other actuators. For instance, with fuel modulation, as I talked about at lower frequency. That has closed loop on it. There's a sensor to get the right feed and so on. And this, let's see, early stage, so we're not there. In fact, I mean, I think one question is, since we don't yet quite understand the mechanism by which the plant is affecting, we don't know what to close the loop. So before we can close the loop, it's good to kind of get a survey of all the conditions under which the plasma can affect the fluid in the way we want it to affect the fluid, and hopefully use that as some kind of feedback loop to optimize it.
And maybe let's thanks the speaker again. This is wonderful. This is wonderful.
Good.
I
Good.
yeah, I already can raise a